Alright students, so for the last 2 weeks of our class and our time together, we're going to be talking about spectroscopy. So this is our first introductory video to spectroscopy. So what do you think about when you hear the word spectroscopy? What do you think it means? If I asked you to define spectroscopy, what would you tell me that it means? So I would define it as the measure or study of light matter interactions. And through the study or the measure of light matter interactions, we can learn about, usually the matter is what we're trying to discern information about. Typically we have control over the light. So we generate the light from a light source. We know what our light looks like, how it behaves, and by interacting it with matter, which might be atoms, it could be molecules, it could be a solution containing several things. The idea is to learn about the matter that the light is interacting with. And there are many types of spectroscopy, but let's first talk about light. Light is an electromagnetic field. So hopefully you remember that from physics. And so what that means is the electric part, or the electronic part of the field, the electric field, is oscillating along the axis of propagation, and it's changing polarity, so positively charged, negatively charged, negatively charged, as it oscillates regularly in time and space. And we can think about 90 degrees perpendicular, right? So thinking about offset, also propagating in the same direction. We have another oscillating wave, which is the magnetic field. So the magnetic field also oscillates. And so we have these two waves, or really one wave acting together, but two parts. And the magnetic field is also oscillating positive, negative, And either the electronic part or the magnetic part can interact and interrogate matter. Sometimes both. But usually, and for most of our types of spectroscopy that we'll talk about in this class, we're thinking about the electric field interacting with matter. So while we can cause the magnetic field to interact with matter, it turns out that there are complications there. So almost always we're thinking about the electric field interacting with matter. And so it's important to remember that as we go through either time or space, that electric field is constantly changing polarity. So what might the electric field, as it changes its polarity, interact with in an atom or a molecule or a solution? What might we think about? Specifically maybe molecules here. The easiest picture is a molecule. What might it interact with in a molecule? So we can think about the polarity of light interacting specifically with the dipole moment of a molecule, which also has a positive end and a negative end. So mu is what we normally use to represent the dipole moment, or the dipole of a molecule. And even nonpolar molecules can have induced dipoles or polarizability. And so this can also interact with polarizable things that can be induced to have a dipole. So here we're going to think about going back to perturbation theory. We're going to use our light interaction with the dipole moment or the polarizability. It could be an induced dipole moment from a polarizable atom or molecule. We can think about that interaction as being a perturbation term to our Hamiltonian. So our Hamiltonian, when we think about spectroscopy, is always our H hat naught, which is just our normal, regular Hamiltonian for our system. So if we're thinking about measuring a vibration, our normal Hamiltonian would look something like a harmonic oscillator. And then we have our perturbation term to the Hamiltonian, which is going to involve the dipole of the molecule, which is direction specific, so this is a vector, times the electric field oscillating in time of the electromagnetic field, or the light, right? The electromagnetic field of the light. And so this electric field, as it oscillates, again, this also is direction specific, it's a vector. So we do have to think about how our molecules are aligned within the electromagnetic field of the light. So the electric field is also oscillating in time. Time is important here. So again, As I mentioned a minute ago, light can also interact with polarization of a molecule. So anything that's polarizable can have an induced dipole moment, which would take the place of that mu vector. But notice that this perturbation term of our operator depends on time. So often when we think about spectroscopy, we are also thinking about time dependence, or the time-dependent version of the Schrödinger equation. And so we didn't spend a whole lot of time working with that, because it turns out that including time makes those differential equations much, much more complex. And so we didn't use time much in this class, but we did mention what that version of Schrödinger's equation looks like. So this is going to depend on time. That might also be your hint that we're not going to do this calculus by hand either. And so we're going to define something else now, which is the transition dipole moment. So all of spectroscopy depends on transition dipole moments. And the transition dipole moment is the probability of a transition from a state we call 1 to a state we call 2 actually occurring. So what is the probability of a transition from one state to another? And so we always call this mu12, or we could replace the 1 and the 2 with specifications of the state we're looking at. But say we're just calling them arbitrarily 1 and 2, or initial and final, we could have also used. So we have this mu12, and it's equal to the integral of psi 2 star, so the state we're going to, or the final state, mu z operator acting on psi 1, or our initial state, integrated over all space. So note that the initial state is always the one that is operated on. And what is this mu z hat, or this transition dipole operator? So mu z hat is going to actually depend on the kind of transition we're trying to measure or induce, or the type of spectroscopy we're doing, right? We could say that sort of either way. And so this transition dipole operator is going to be specific to the type of spectroscopy that we're dealing with. So let's talk about some types of spectroscopy in sort of a general and broad sense. So all types of spectroscopy depend on light or electromagnetic radiation interacting with matter, and all types of spectroscopy depend on a transition dipole moment being non-zero, or having a non-zero probability of transition. So what are some broad types of spectroscopy? So one of the things we've talked about in this class, both with the photoelectric effect way back in week 1, as well as when we talked about photoelectron spectroscopy in terms of term symbols, back when we talked about atomic term symbols not so long ago, we talked about ionization. And ionization requires what's called a vacuum ultraviolet, or all the way through X-ray light. So vacuum ultraviolet is just really high energy ultraviolet. And so we're thinking about frequencies of light that are greater than or equal to 10 to the 16th hertz. Another thing we've thought about and actually done in lab when we were in person in lab was bound electronic transitions. So a bound electronic transition, if we think back to our lab where we played with dyes, back with particle in a box, we were measuring bound electronic transitions of those dyes, specifically of the pi bonds in those dyes. And so bound electronic transitions require ultraviolet and visible light. And so this would be frequencies on the order of 10 to the 14th to 10 to the 16th hertz. Note that if we're trying to induce a core to a very, very high unoccupied state, we might actually be getting closer to that vacuum ultraviolet, right? So we might actually be getting a little bit higher in energy if we're dealing with a very core to very high energy transition that is considered bound. So we can also think about vibrations, which is another thing we've measured in the lab before. Vibrations require infrared light, which is on the order of 10 to the 13th to 10 to the 14th hertz in frequency. And we can also measure rotations. And rotations are going to require microwaves through far infrared. So far infrared is going to be low energy infrared light. And so this is going to be frequencies on the order of 10 to the 9th to 10 to the 13th hertz. So we can see that rotations are really, really small energies, vibrations are bigger energies, and electronic transitions are even bigger energy transitions. We can also have some weird hybrid spectroscopy techniques. And so we can think about having vibronic spectroscopy or vibronic spectra. Vibronic spectroscopy is going to be an electronic transition which contains vibrational information. We'll come back to that. All right. So we can also have a hybrid between vibration and rotation, which is called rho vibrational spectroscopy, which is vibrational spectra that contains rotational information. Another interesting, a less talked about, your book doesn't mention it at all, but something that does occasionally happen but is very hard to do and is usually only done for diatomic molecules, because beyond that it becomes very difficult, is rho vibronic, which would be electronic spectroscopy containing both vibrational and rotational information. This is pretty rare, and so your book doesn't talk about it. So how and why, right, whichever question you want to ask there, how or why do hybrid spectroscopic techniques occur? So there was this diagram I drew you. I'm going to try to draw it again here. Once upon a time, this was a while back. I don't remember exactly in what context this came up in class, but I remember drawing this on the board before we left campus. So here we have energy going vertical. We have two what look like potential energy curves. And we're going to say that those potential energy curves are electronic energy levels. And the most probable place for the electronic energy to be defined is in the middle of the parabola, right? The lowest energy of the parabola, or not quite parabola, but maybe Morse potential. Within each of those two electronic energy levels, there's a whole set of vibrational energy levels. So every electronic energy level contains its own unique set of vibrational energies. And within each vibrational energy level, there's a unique set of rotational energies. So the green is the rotational energy levels, and there's an entire set for every vibrational energy level, and there's an entire set of vibrational energies for every electronic energy level. And so these are very much nested, right? The big energies, the things that are really far apart in energy, are the black curves or the electronic transitions. The things that are closer in energy would be the purple or the vibrational energy levels. And the things that are closest in energy or require the least amount of energy for transition are rotations. But we can think about if we had a transition from somewhere in here to somewhere up here, we could think about having the information of the vibration that we start from and the vibrational energy that we land in that excited electronic state. And that's what we're going to call vibronic energies, when you can see the evidence of the vibrational or of the rotational energies that change, right? For rho vibrational, we could think about maybe going from here to here and thinking about having that information within the vibrational energy spectrum of the rotational energy level that we started from and that we ended in. And that's kind of interesting. So we will be looking at these hybrid types of spectroscopy because they're actually very common as well. And so the rest of today, we're going to be talking a little bit more about electronic spectroscopy, going into a little more detail than just photoelectron spectroscopy that we've already talked about. The rest of this week, we'll then be going to vibrational, then vibronic, then rotational, and rho vibrational. And then we'll talk a little bit about modern spectroscopy. If there is a modern spectroscopy theme that you really want to make sure we hit on, please let me know. Also, we'll be talking a little bit about NMR and EPR. All right.